Hi everybody. It is now time to talk about Coulomb's law. Coulomb's law is very similar to Newton's law of gravitation. It is what gives the force between two charged particles based upon their charges and on their separations. So, without further ado, Coulomb's law says that the force of electrostatics of particle 1 on particle 2 is equal to K Q1 times Q2 all over the distance between the particles squared. Okay? And again, this looks a lot like Newton's law. You get the 1 over distance squared relationship. You get the product of two things at the top. It used to be masses. Now it's charges. Q's are charges. D is distance. And K is Coulomb's constant, which is 8.89 times 10 to the 9th, and the units must be newtons meters squared per coulomb squared to get out the units you need. Okay? So, for example, say we did a 1 coulomb charge and an 0.5 coulomb charge, and they were 0.1 millimeters apart. We would say that the force of electrostatics of charge 1 and charge 2, by the way, you'll notice this is going to be symmetric. I'm going to get the same force magnitude for both of them, which is what Newton's third law says I should get. K times 1 coulomb, times minus 0.5 coulombs, all over 1 times 10 to the minus 4th meters. That's 0.1 millimeters right there. It's 1/10 of 10 to the minus 3 millimeters squared. Okay. If you do the math, I think you get 4.45 times 10 to the holy cow 17th newtons. Okay. It's a combination of this K value and this, that should be squared. This minus 4th getting squared. Okay. So, going back to Coulomb's law, F E is equal to K Q1 Q2 over D squared. First of all, the force direction, the vector of this force, points along the line between them. So, just like gravity, this points either one particle towards the other or one particle away from the other. Second point, if these charges have the same sign, this is an overall positive force, which we take to mean the things are repulsive. This is true if either both of them are positive or both are negative, because then the negative signs cancel, of course. If the charges have different signs, and it doesn't matter which one's Q1 and which one's Q2, you get a negative force, and we take that to mean the two are attracting each other. Okay? The signs on Coulomb's law will tell you if the force is attractive or repulsive. This is a lot like Newton's law of gravitation. One major difference I need to point out, however, is that these are not masses. This seems perhaps silly and obvious, I'm telling you this. But there were many times when we were doing things with Newton's law of gravity, or just gravity, like on the Earth, where the mass canceled out. For instance, that's what gives us the uniform acceleration of every body falling near the Earth's surface of g equals 9.8 meters per second squared. That's not going to happen here. The mass that's leading to inertia in F equal ma is not the same as the charge in here. So they're not going to cancel. And so different particles in the same sort of environment are going to feel different amounts of acceleration. Okay? That doesn't happen with gravity, oddly enough. Okay? Finally, I'm just going to tell you right now, you're going to see this sooner or later, that K has another way of being written. 1 over 4 pi epsilon naught. Okay? Where epsilon naught is equal to 8.85 times 10 to the minus 12 coulombs squared per Newton meters squared. Okay? Why would you do this? Well, for one thing, you get a 4 pi d squared, which kind of looks like a surface area of the sphere of radius d around one charge. It turns out epsilon naught, however, it's called the permittivity of free space, is the more important quantity between k and epsilon naught. It is actually the one that pops up in the equations more naturally. We'll start seeing it in about 2 weeks, I think. And then it'll be the one we're using all the time. For practical purpose, for calculating force, it's easier to use K. But once we start talking about other equations, epsilon naught is going to pop up a lot more often. Finally, I want to point out that the value of K is much bigger than the value of big G from Newton's law. This was like 10 to the minus 11, and this is like 10 to the plus 9. So there's around 20 orders of magnitude, 10 to the 20th power between these. What does that mean? Well, a lot of people say it means that gravity is a very weak force and electrostatics is a very strong force. I say it doesn't mean anything. If we'd chosen the unit of charge differently, this would have a different value and it would be very small. If we'd chosen the unit of mass differently, this would have a different value and could be much larger. In a specific situation, we can talk about which is a more important force. For instance, protons and electrons bound together in atoms. Which one's the more important force, gravity or electrostatics? I'm not going to tell you. You're going to have to calculate that. But it is worth remembering, though, that these Val numbers are going to often be very, very big. Or you're going to be looking at very, very small charges. Okay? All right, that's all I have on Coulomb's law. I will see everybody in class.